In this video, we'll be taking the basics of geometry, and then we'll be looking at angles, the types of angles, triangles, and a number of other things. So as you already know, an angle is formed where two lines meet. All right, so if I have two lines meeting at whatever point or under whatever case, we'll say an angle is formed. So I could have an angle formed in any manner. Okay, I could simply have an angle formed this way. But however it is formed, wherever two lines meet, we'll see an angle is formed. So I'll be going in accordance to the slide real quick. So we got types of angles as the first subtopic. So it says that there are 360 in a full turn, 180 in a half turn, and the 90-degree in a quarter turn. It says a quarter turn is also called a right angle or a perpendicular. Now, talking about an angle formed in a full turn. So I would have a line this way. So if I have an angle starting off from this end, if it goes all the way around, we'll call it a full turn. And then we'll say the angle formed in that manner is simply 360 degrees. Now, similarly, second part says an angle formed in a half turn. If I similarly have a straight line and then I have an angle formed from this end, if the angle goes all the way, just halfway through the full turn, we see an angle 180 degrees formed. And then a quarter turn will be 1/4 of a full turn, of course. So if I have an angle, gone quarter turn, that would mean going this way and then stopping somewhere here. And then that would be an angle 90 degree. So that should not be a problem. Now it says, then you can see it shown in the diagrams there. So that is the full turn, the half turn, and then the quarter turn shown. It says the right angle is known by a small square. So whenever you see a representation of this order, then you know that that's referring to a right angle or a 90 degree is formed. They may or may not indicate the 90 degree number, okay, but then we're meant to see a small square between a perpendicular line or between a vertical and a horizontal line. We see a 90 degrees formed, and we call it a right angle or a perpendicular. Now looking at the first example, now it says calculate angle C. So in that diagram I have a quarter turn, okay, of an angle formed there, and that is representing an angle 90 degree. Remember we said the angle formed in a right angle is 90 degrees. So practically, the diagram shows a 90 degree divided into two parts or divided into different parts. All right. So whatever uh, whatever part the angles is divided into, just know for a fact that an angle formed through a quarter turn, the sum of angles formed in between that turn is 90 degrees. So we can practically say that C plus 20 degrees would equate to 90 degrees, which represents the quarter turn. So if I were to solve for C, all right, I would simply subtract 20 from both sides, or as we would usually say, I would move 20 to the other side. And when 20 crosses over to the other side, it becomes a negative 20. So I would have C then to be equal to 90 minus 20, and that would become 70 degrees, making C equal 70 degrees. I believe that's quite clear. So this principle applies for every other um, of this angle too. If I similarly have an angle going through half turn, and then it is divided into different angles, as in this case, I have a straight line, and then I probably have an angle, let's say C, and then an angle, let's say 120 degree. And I'm required to calculate for C. All right, knowing fully well that this angle, okay, is on a straight line, all right, that would simply mean that the sum of angles on a straight line is 180 degree. So that practically means that C plus 120 should naturally equate to 180. So if I similarly subtract 120 from both sides, I should have C to be equal to 180 minus 120, and that will rightly give me 60 degrees for C. And that was how all of this goes. Okay, lastly, if I similarly have an angle formed across or around a full turn, all right, I would similarly have the same case, or I would similarly do the same thing. But we'll see multiple different examples on this in the next video. Now, moving on in accordance to the slide, it says there are three different types of angle. We have the acute angle, the obtuse angle, and then we got the reflex angle. It says an acute angle is an angle that is less than 90. So every angle less than 90 ranging from 0 up until, let's say, 89 or just below 90. We'll call them an acute angle. And then we'll categorize angles between 90 and 180 degree. Angle that exceeds 90 degree but are less than 180 degree, we call them obtuse angle. And that is represented grammatically likewise. And then we have reflex angle, which are angles that are greater than 180 but less than 360. So that's about that for that. Now moving on to the next part, it says angles at the point and on a straight line. So as I described before, we're going to be looking at examples on this going forward. First of all, we have angles at the points. It says angles around the point add up to 360 degree. Since this fact can be used to calculate missing angle. As I said earlier on, angles around the turn basically means you're going all the way around. So practically from this point all the way back to that point. The sum of angles covering that space or covering that point would equate to 360 degree. So practically it means A plus 60 plus 95 then plus 105 should entirely sum up to 360 degrees. All right, so if you are required to find A, then you simply, subtract all of this from this end so that this becomes A equals 360 minus 60 minus 95 minus 105. So whatever you have for this answer becomes the value for A. Just make sure to understand the principle around this. So similarly, you apply the same principle for angle on a straight line. It says angles on a straight line add up to 180 degree. It says this fact can be used to calculate angles, okay, missing angles. Now, as I said or I explained earlier on, this is a straight line, all right? And then this is similarly a straight line. Now, you have to be careful with the one you approach first. Now, I am required to calculate angle B and C. If you look at straight line, let me call this straight line 1 and I'm going to call the other one straight line 2. Now, if you look at straight line 1 carefully, I have angle B and angle 30 degree. So I am choosing to solve for straight line 1 first because straight line 1 only has one unknown. Okay, on straight line 1, I can easily solve for B. So on straight line 1, I have B and 30 degrees summing up to 180. So I could write that as B plus 30 degree equals 180 degrees. Right, so if I subtracted 30 from both sides, that makes my B equal to 180 minus 30, and that will rightly become 150 degree. So practically, I can replace B on straight line 2 as 150 degree. So this is straight line 2. So instead of having a B there, my B is now, 150 degree. So I have on straight line 2, following the same principle, the sum of angles on a straight line would rightly sum up to 180 degrees. So that would rightly be C plus 150 degrees equals 180 degree. So if I subtract 150 from both sides as I did before, I would have C to be equal to 180 minus 150 degrees. And that would rightly make C equal to 30 degrees. So I want to believe this is very clear. Um, so I'll be wiping out this part. Now it says notice that vertically opposite angles are equal. That will be a principle we'll look at later on. But that would rightly be a way to solve easier. All right. So we have okay, don't worry, I'll speak about it later on. Now we have angles in parallel line. This is probably one part of geometry that people find quite difficult and confusing. But I assure you though that is nothing serious. Now it says parallel lines are lines which are always the same distance apart and never meet. Now these are known principles or these are known theories for parallel lines. You have to understand what parallel lines particularly refer to. Now, when you have two lines, all right, that are, we say they are equidistant from each other, meaning they are at equal distance all through their motion. Okay, if these lines were to move, or if this line were to continually move, there's never a chance that they will meet. So they remain at equal distance from each other at every point or at every time. All right, so that goes on to mean that they can never meet. Those are parallel lines. And then when you see two parallel lines, you usually see them indicated by arrows. You usually see arrows over them. So if you want to know if lines are parallel, they would have similar arrows over them, something like this. They would just be similar. Now, on parallel lines, all right, when you have two parallel lines, when a line, okay, crosses or when a line crosses two parallel lines, we say quite a number of angles are going to be formed. And we call that line an intersecting transversal. All right, and that is shown diagrammatically there. Now it says when a pair of parallel line is cut with another line known as an intersecting transversal, it creates pairs of angles with special properties. Now we're looking at those special properties in a moment. Now first off, we have the corresponding angles. Know for a fact that corresponding angles are equal. Now what are even corresponding angles? It says the line makes an F shape. Notice that the F shape can be upside down or back to front. Now check out this diagram real quick. Now this is okay. Wait, let me make that clear. All right. So these are diagrams showing corresponding angles. Remember, it says it makes an F shape. Now let me draw that boldly. Now this is a parallel line. These are parallel lines. All right, if I have a transversal over this parallel line, let me give this an easier or a better understood explanation. So I practically call them parallel lines. I'll call them corresponding angles. If the angles lie on similar positions on the lines, on each of the lines. Remember, this is line 1 and this is line 2. Now, the part or the angles, okay, that are similar, all right, on angle on line 1 and line 2 are said to be corresponding. What does that even mean? Now look at this first transversal. This angle would be similar or would be the same angle as this on this diagram. All right, because look at that position. If this is A, this will similarly be A. All right. If the one under A would also be the same thing as the one under A here. So if this is B, they would similarly be B. The one on the left hand side, lower part, if I indicate that as C, this would similarly be C on the lower part of the second line. If I made this D, this would similarly be D. So we're going to say each of these angles are corresponding, meaning they lie on similar position on the two lines. That's practically what this means. And if you look at that carefully, they similarly form up an F. They similarly form up an F as indicated in the notes. So this is just okay, chilling. Just make sure that what there are angles that lie on similar positions, all right, on each of these lines, and then that would be quite understandable. Now we got alternate angle. Okay, I think this one will probably be a very popular one. We usually say an angle that forms up a Z, all right, are equal. So we say alternate angles are equal. The lines make a Z shape, which can also be back to front. So practically we say it could be this way, okay, this angle corresponding to this angle, or it could be this way. All right, this angle corresponding to this angle. So whichever it may be, the angles are said to be alternate. All right, mind you, the Z could be an N too. Just make sure that this is a parallel line, this is a parallel line, and then this vertex, all right, are equal. All right, parallel lines are, or alternate angles for that, are always equal. Now we got vertically opposite angles. We're going to use this in an example, so for you to better understand what all of this is all about. But then we have vertically opposite angle. As I earlier mentioned, vertically opposite angle are practically just angle that forms up a Z. All right, if I have this, all right, we'll say this is vertically opposite to this, and these angles are said to be equal. So just like that, this angle is vertically opposite to this too. Okay, that makes them likewise equal. So that is that for that. Um, so those are angles formed on a parallel line. So in the next video, I'm going to take examples that would largely buttress each of those theories. Now we got triangles. Okay, you're probably familiar with triangle. Okay, triangle would be a quadrilateral with three sides. Okay, and then there are quite a number of principles that bound triangles. Okay, but then beyond all of those, or before all of those, you have to understand what a triangle actually is, and you have to understand the various types of triangle we got, and similarly the various principles that applies for each and every one of these triangles, and of course the properties of each of these triangles. Now it says a triangle is a 2D shape with three sides. It says there are four different types of triangle, okay, of course with different properties. We have the scalene, the isosceles, the equilateral, and the right angled triangle. Now, looking at each of their properties one at a time, it says a scalene triangle has three sides of different lengths and three unequal angles. So this is a uniqueness for scalene triangle. Okay, each of these triangles would usually have properties that differ them from each other. All right, so a scalene triangle is said to have three sides. Of course, all triangles have three sides, okay? But then for a scalene, each of the sides have different lengths, okay, making them similarly have different angles or unequal angles. So that will be that for a scalene triangle. Now we have an isosceles triangle, which is said to have two sides of equal length. It says the dashes on the lines shows they are equal in length. So these indications, all right, whenever you see these indications on triangles, it tells you that they are isosceles, meaning these two sides are of similar length. So if this were to be 5 centimeter, this will similarly be 5 centimeter. Now this one could be anything aside 5. This is what defines an isosceles triangle. Now, it says the angle at the base of the equal sides are equal. So, alongside the equal lengths or the equal sides, they similarly have equal base angle. We call them base angles. So those indications, those green indications, tells you that those two angles are equal. So if this were to be 30 degree, this will similarly be 30 degree. Next up, we have an equilateral triangle. It says an equilateral triangle has three sides of equal length. All right, and then you can see the indications too. The dash, all right, the dashes indicate that each of those lengths are equal. So if this were 5 centimeter, this would similarly be 5, and this would similarly be 5. All right, so coupled with their equal length, they similarly have equal angles. So each of the angles are equal to each other. I will explain how you estimate the values of those in a bit. Now, we have the right angle triangle too. It says the right angle triangle is a triangle that has a right angle. Remember, earlier on we spoke about a right angle being a 90-degree angle, a perpendicular. So we say something is a right angle triangle if it contains a 90 degree. All right, that's practically that. So don't forget the indication there, that small square at the base right there, is what defines or what tells you that that triangle is a right angle triangle. Make sure to be able to identify or to differ or to tell apart each of these triangles. Now that is that for that. Now it says labeling angles and side. I think this is one very important section in triangle. All right. Many a times you would see angles written in this order: angle B A C, angle A B C, angle B C A, and then you can't quite tell, what each of this means. Many a times you just go ahead and write whichever you like, okay, without fully understanding what each one refers to. Now it says by the slide it says letters can be used to label angles. It says AB and AC align segments, as you can see in the diagram, and then they meet at a point, meaning an angle is going to be formed between them. Now it says AB joins the points A and B. So the angle between AB and AC is labeled BAC. Now, whenever you label these angles, or whenever you label angles, you want to make sure that where the angle is at is usually in the center. So in this case, I'm going to call it BAC simply because A is what carries the angle. All right, so I'm practically doing angle BAC and not angle BCA or whatever, because I'm not using angle BCA because the angle does not lie on C, but rather it lies on A. So this will be correct while this will be incorrect. And that is how that goes. So you can only use BCA if the angle directly lies on C. Now moving further, it says the angle can be written as BAC or BAC or angle BAC. So whichever you use, just make sure though that the angle, right, or the part that carries the angle lies in the center. So if you look at these three guys, you find out that A is placed centrally to indicate where the angle is at. So that is that for that. Now, talking about our other principles of triangles, we have interior and exterior angles. Now, it says the angles inside the shape are called interior angles. So, interior meaning inside, all right, while exterior is more or less like external, internal and then external, like that. So, it says if the side of a triangle is extended, the angle formed outside the triangle is said to be an exterior angle. So, by the diagram, G represents the interior angle of this triangle, while H, formed outside the triangle, represents an exterior angle. So if you look at that closely, you realize that G and H lie on the same straight line. All right. So from our earlier stated principle, G and H should rightly sum up to 180 degree. Or furthermore, we'll say they are supplementary. Now, it says the interior angle and its corresponding angle always adds up to 180. So know that similarly as a ground principle. All right, make sure to pay attention to all of this principle because on the long run they would come in handy. So moving further, it says the sum of interior angles in a triangle. Now, it says the sum of interior angle in a triangle is 180 degree, practically meaning that sum of angle inside the triangle would usually sum up to 180. It said to prove by the diagram, A plus B plus C would equate to 180. It says first, draw a parallel line to one side of the triangle. DB, remember the angles we looked at earlier on, angles formed in a parallel line. So I have a parallel line, all right, formed around a triangle like this. Now remember, uh, if this is a transversal and this is a different transversal, all right, the angle formed here would be equal because they are alternate to each other. They form opposite. Similarly, if this is E and this is C, the angle here would similarly be equal because that is similarly an alternate angle, making E equals to C and D equals to B. Let me rub that off. So A plus D plus E is said to be equal to 180 simply because they are all lying on the same straight line. All right. Now, if that is the case, and I already said D equals B and E equals C, that would similarly mean that A, B, and C would also be equal to what? 180 because I could rightly rewrite B as D and C as E. And we already established that across this straight line, A, D, and C, what's that? C, E, rather, they sum up to 180. All right, so that would similarly make A, B, and C sum up to 180, and that would make the sum of interior angles proven. Just know as a ground rule that the sum of angles inside a triangle add up to 180. Since this fact can be used to calculate angles. Now, going further, we have quadrilateral. Now it says a quadrilateral is a 2D shape with four sides. These are, or there are six special quadrilaterals with different property. We have the square. The square is drawn or is shown diagrammatically right there. It says a square has four sides of equal length and it also has four right angles. So between the vertices of a square, you have right angles right there, 90 degrees. And it says the opposite sides are parallel and then it says the diagonal bisector of each or the diagonal bisect each other at right angle. So practically, if I have a diagonal is just a line that divides a shape, okay, into two equal parts. So practically, if I have a diagonal across this end and I have another diagonal across this end, we're practically saying each of these diagonal they bisect one another at 90 degree like this. That's what that statement is talking about. Now we have the rectangle too, which is another quadrilateral. It says a triangle in shape or in view is similar to a square, only that it is somehow more broader or more unequal. Or let me say it is quite unequal than a square. Now, what differs a square or what differs a square from a rectangle is in the fact that a square has all of its lengths equal, but that's not the case for a rectangle. Since the rectangle has two pairs of equal sides, right? So that practically means the opposite sides of a rectangle are equal. All right. So if this is A, this will similarly be A, and if this is B, it will similarly be B. Now it says it similarly has four right angles like a square, and then the opposite sides are parallel, just like a square. And similarly, it says the diagonal bisects each other. Right. So moving further away, so we have a parallelogram. Let's stop. It says the parallelogram has two pairs. Okay, let me rub this off first off. So it says a parallelogram has two pairs of equal sides. Then it says it has two pairs of equal angles. The opposite sides are parallel, while the diagonal bisect each other. So these are a known principle for a parallelogram too. Okay, unlike rectangles and squares, all right, the vertices of a parallelogram do not contain right angles, and that's what particularly differs a parallelogram from those two. All right, but then they similarly have four sides, making them a quadrilateral, and then their opposite sides are said to be parallel. Remember, when we have parallel sides, okay, when a transversal crosses or when a line bisects or when a line crosses those parallel lines, okay, those four angles we or those three angles we earlier treated would, you know, come into play. They alternate the corresponding and the vertically opposite angles. So those principles will be applied across all of this. Now we have a rhombus. It says a rhombus has four sides of equal length. It has two pairs of equal angles, and it says the opposite sides are parallel. And of course, lastly, the diagonal bisect each other at right angles. So that is very similar to a parallelogram in view, but then they have quite a number of differences. Now, moving on. Now, what differs a rhombus, by the way, from a parallelogram is in the fact that while a rhombus, okay, the bisectors of a rhombus, okay, are 90 degree, meaning the diagonal bisector of this guy. Oh shit, sorry, let me rub that off. The bisector, okay, the diagonal bisector of this guy bisects it at 90 degree. All right, but that's not the case for a parallelogram. The bisector may not be 90, okay, or they do not be, they're not 90 degree. They are, lesser than, or even more than. Now, we have a kite lastly. It says a kite has of two pairs of equal sides. All right, it has one pair of equal angle, and the diagonal bisects at right angle. So, like a rhombus, diagonal for a kite similarly bisects at right angle. Just make sure you're able to tell each of these quadrilaterals apart. So, the sides, okay, above here are equal for a kite. So, we have two isosceles end there. So, this also equal to each other. All right, and then we have a bisector, diagonal bisector at that point, and these bisectors are 90 degree all around. So that's that for all of those. Lastly, we have polygons. It says a polygon is a 2D shape with at least three sides. Okay, so from three sides up to infinity, we call those shapes polygons. Now we have two types of polygon. We say a polygon could be regular or irregular. Now it says if the angles are all equal and all the sides are of equal length, we call such a polygon a regular polygon. And then if the opposite is the case, we call them irregular polygons. Now, talking about interior angles of polygons, it says to find the sum of interior angles in a polygon, divide the polygons into triangles. It says the sum of interior angles in a triangle is 180. So to find the sum of interior angles of a polygon, multiply the number of triangles in the polygon by 180 degrees. So I'll probably give a formula for this going forward. The formula I would rightly give you will simply just okay. I think there's a formula stated later on. Now it says calculate the sum of interior angle in a pentagon. So the pentagon contains three triangles. Now if I were to draw a pentagon, I think I should have something like this. Pentagon is just a five-sided shape, right? So I should have this. Don't mind my diagram, please. Let me try to give a better artwork. So a pentagon should be something like this. Yeah, five-sided. So if I went on to divide this guy into what's it called? Into triangles. All right, I would have this. Yeah, something like this. So practically, I have been able to form up this pentagon into three triangles, or I've been able to divide this pentagon into three triangles. So as per the rule, to calculate the sum of interior angle, knowing fully well that each of the triangles sum up to 180 degree. Remember, each of the triangles sum up to 180. We mentioned earlier on that the sum of angles inside the triangle is 180 degree. So each of this triangle has the sum of their angles equated to 180 degree. And then of course we have three triangles all together. So that would rightly mean that the sum of angles inside the pentagon will be three times each of the triangles. And that would rightly equate to 540 degrees. Okay, so you may or may not use this method to solve this. We also have a formula method that helps you probably easily or easily solve the sum of angles in a pentagon or sum of angles in polygons generally. Now it says the number of triangles in each polygon is two less than the number of sides. So pay attention to that details there. So the sum of the number of triangles in each polygon is two less than the number of sides. All right. Now, by formula method, it says the formula for calculating sum of angles in or the sum of interior angles is given by n minus 2 multiplied by 180. So if I do not want to do this, I can rightly do this too. So for a pentagon, in the case I did earlier on, number of sides for a pentagon is 5. So I rightly have 5 minus 2 into brackets 180. So I would have 3 multiplied by 180 eventually, and that leads me back to here. So my answer becomes 540, 540 degrees. And that'll be that for that. All right. So as I said before now, in the next videos, we'll be solving example questions across each of those principles. So I would indulge you to go on and go over every of the principles we've spoken about across this slide. All right. So I will go on with the examples. You can rightly follow up. Just make sure to digest every single principle we've spoken about, every single theory we've um, spoken about. Digest all of those, and then you can rightly apply all of those in the examples we'll be looking at in the next video. Um, I'll see you when I see you. Bye for now. Carbon. Carbon. Mm. Which one be continue to record? Teach your class now. Why
As you
you
dey
doing?
around now, na because say you dey do video na why I go.
You know, if you say me, I dey around for one particular purpose, that will achieve.
Which purpose?
So you just sit there, just useless.
No. Now I think say you dey around now.
I dey around, but na because I wan do something, I wan no go out.
This thing don cut.
Wetin cause? No, I mean when I stop the record, na him show this thing. Do
You got
continue to
20
record
minutes of
first.
audio recording time in this document.
In this document, like it is.
I don't understand.
Do click continue to record. So stop am normally the way you will.